Even though this lesson is about pointers and references, I thought it's an appropriate time to introduce recursive functions. I did not want to talk about the memory segments and the stack in Module 101. I felt this was unnecessary since we would only use both the stack and the heap in this module. Of course, that would also lead to some duplicated work and explanations, so I decided to discuss all of that in this lesson, again where we talked about the memory segments, the difference between the stack and the heap, and so on. Now, since you should have a basic understanding of the stack and how stack frames get pushed onto the stack when we call functions, you should be able to follow along with this lecture. I could present an entire lesson on just recursion, since there are some complex examples. In some lessons it's important to understand what I'm referring to when I say some function will be called recursively. So the goal here is just to introduce the topic, and actually in the future I might add a bonus lesson with additional examples on recursion, since you do have some interesting and complex examples. But really, when you have the fundamentals down of what I'm going to show you in this video, you should be able to apply that to solving other problems, and that's really all we need to move forward here. An understanding of this will be important in upcoming lessons, so in the lesson on operator overloading, for example, because sometimes you have to check out for recursion. Recursion can lead to your program crashing if you run out of stack memory because you are calling the same function over and over again, so I'll show you an example of that later on in a quick illustration. A recursive function is a function that calls itself, and a typical example is when you calculate the factorial of some value. So if n is non-negative, then the factorial of n is written as n with an exclamation, and it can be defined as 0 factorial, so 0 exclamation, that will be 1, and then n factorial will be n times n minus 1 in brackets. You'll see that is also a factorial calculation, and that is where the recursion comes in, because you're going to calculate that, and within that calculation you may have another factorial calculation. I have an example of what I mean at the bottom here. Factorial of 3 is written as 3 exclamation and is calculated as 3 times 2 times 1, and that will give you 6. With a recursive function we have a base case and a recursive case. Now the base case is the case where the solution is obtained directly. Every recursive function definition must have a base case, because the base case stops that recursion. Now from the factorial example, the factorial of 0 is going to be 1. It's just a code expression here. Let's have some function, factorial. We pass it an argument of 0, then we expect to get back 1. So expect that to return 1. Then we also have the general or recursive case. Now for this, the solution is going to be obtained through recursion. The recursive case must eventually reduce to the base case to again stop the recursion. Now from the factorial example, the n factorial expression is the recursive case, because you can see again we have between brackets n minus 1, and that is also factorial, so that can lead to another factorial calculation. It's just another expression example. When you call the factorial function and you pass it some value, let's call it n, then what is it going to return? It's going to return n times the factorial again of n minus 1. So you can see here why this is a recursive case, because to give us the example, right, we pass in n initially, that will have to call that factorial function again and do another factorial calculation, and that could lead again to another factorial calculation and so on. Okay, here's the factorial example. I have the function factorial. It's going to return an unsigned long. If you pass in values 8 and above, you can get huge values back. For that reason I went with the unsigned long, and the formal parameter is also an unsigned long, that is n. In the body of the function, if you remember, we need a base case. What is the base case for the factorial? Well, if it's the same as 0, then return 1. Otherwise it's going to do this calculation here, which is the recursive case. It's going to return n times the factorial of n minus 1. Now of course when it reaches this here, it's going to call this same function again. It's going to execute the code in that function. That function might call this function again. Eventually we'll get back to the case where n is equal to 0, and then it's going to return 1. So this is how we stop that recursion. To test the function, in main I have this output, console output, factorial, and in this case I pass in an argument of 3. Build and run that and we get 6. You can test that with 0 and you'll get 1. If you pass in 2, that function should return 2 as well, because this is going to be 2 times 1. Whereas if you pass in 3, that is going to evaluate to 3 times 2 times 1, which is why we get 6. For this example, I have the stack illustration again, with the example program to the left and the stack to the right here. we start with main on the stack. In the console output statement, we invoke that function. We do cout and then factorial 3. That will push a stack frame onto the stack. The argument is 3 and this is passed by value, so the formal parameter n is going to be initialized to 3. Since the argument is 0, we are not going to return 1. We move to the else part, which is the recursive case. N here is 3 again, so 3 times factorial of 3 minus 1. Because we call that function again, we push another stack frame onto the stack. The argument that we pass in is 2, so the formal parameter n will be initialized to 2. I emphasize this because you have to remember each time we call that function, it's going to essentially create local variables. They act as local variables, but they accept arguments. Of course, you can think if you have many arguments, and you call a function recursively, you keep adding stack frames onto the stack. That will take up a lot of memory. And again, since n is not 0, we move to the recursive case, which means we'll call the factorial function once again, this time with 2 minus 1 as an argument, so we basically pass in 1 as an argument. That is going to push another stack frame onto the stack. This time the argument is 1, so in the formal parameter n will be initialized to 1. Since n is not 0, again we'll do the recursive case. We'll do 1 times the factorial of 1 minus 1, which will push another stack frame onto the stack. Okay, we invoke that factorial function again. This time we pass in an argument of 0, so the formal parameter n is set to 0. We finally have the base case, so it's going to return 1. Program execution is going to return to the calling function, and we pop that stack frame off of the stack. So this function is still executing now, we are still in the body of this function, and since that function returned 1, we now have 1 times 1 as the return for this function. That means this function is also going to return 1. Program execution returns to the calling function, and we pop that stack frame off of the stack. The function still has to finish execution before returning, so we got 1 back from that function call. So 2 times 1 is going to give us 2. So the function is going to return 2. Program execution will again return to the calling function, and that stack frame gets popped off of the stack. That function execution returned 2. So in the body of the function call that we have left here, we return 3 times 2. So we return 6, and program execution will once again move to the calling function, which in this case is main. And we print that out to the console again in that cout statement. This is why I mentioned in previous examples and illustrations on the stack and the stack versus the heap and so on, why it is useful to have a sort of study notebook where when you solve a problem using recursion and you sort of step through what's happening, why it is useful to go and draw a stack, because it's a relatively easy way to step through and see what's going to happen and what it's going to return. As always, you can use some of the debugging tools in Visual Studio. I'll place a breakpoint right here and run the Windows debugger. And then I have the stack actually to the right here, so I don't have to animate and all that stuff. And I'll just step into that line. Execution will reach this line. If I step into that, it will call that function again, and you'll see we get the call on the stack. Step into that. As soon as I step into this line, we'll get another function call on the stack. So step into that, and that is what we get. And now we will start to remove some of those from the stack until we get back to main and we print that value out. As I mentioned, I still find it very useful to draw the stack out and also keep track of the values, so the local parameters. But of course you can make use of the debugging features in Visual Studio as well. Just a few more notes here. You might think, well, I can do something similar using a loop. Well, you can. That is called an iterative solution. And you can use either one of these. I would suggest that you only use the recursive solution when it makes sense. The iterative solution typically involves a loop. The algorithm does not involve recursion, so the function does not call itself in its definition. Whereas with the recursive solution, the function is going to call itself in its definition. The example that we looked at in this video was direct recursion. So where the function calls itself, but you also have indirect recursion, and in that case the function calls another function, which eventually results in calling itself. So as an example, function A calls function B, that can call another function C, which can eventually call function A. That is an example of indirect recursion. Of course you can have function A calls function B calls function A, so that indirect recursion can have many layers. Okay, that is going to wrap up this lecture on recursion. I hope you found it interesting, and I'll see you next time.